Hello, my name is Thomas Purcell. I'm currently an assistant professor at the University of Arizona in the Chemistry and Biochemistry departments, and was formerly a postdoctoral fellow-group leader at the Fritz Institute in the Nomad Laboratory. And today, I'll be introducing you to the SISSO methodology and some recent advances that I made in it while at the FHI and here in Arizona. However, I want to briefly apologize for not being able to attend this session live via Zoom because the time zone difference between Arizona and Europe made it fairly impractical for me to give this talk live. However, after Lucas's talk, I should be able to join the call for Q&A and would be happy to answer any questions of the SISSO methodology then. Before addressing SISSO itself, I want to first briefly discuss the class of methodologies that SISSO is a part of, mainly in symbolic regression. Symbolic regression is a way of approximating a target property for some system as a function f of some set of inputs, here shown as x and y, as an analytical function. For example, sine of 2.3 times x times y plus pi over 4. The reason why this method is becoming increasingly popular in the sciences is that in the model accuracy and interpretability Pareto front, it's normally viewed to be in between decision trees and linear logistic regression, meaning that we can get fairly accurate models that has physical insights in it that we can fairly readily interpret. And on computers, how we actually store the underlying expression symbolic regression found is normally through these binary expression trees. And the reason for this is twofold. One, it is a unique mapping onto an analytical expression without having to worry about parentheses, brackets, or any of that. And two, we can define anything about a given expression by simply doing a proper transit of the trees themselves. And this will actually lead us directly to a stack that we can convert these trees into a set of computational instructions in order to calculate the final property estimates. And how we can think about this is that we have access to different levels of complexity by thinking about the trees themselves in terms of both the height, which is represented by rung in SISSO, and our primary way of describing the complexity. So this basically is called a rung because we think of it as a rung of a ladder. As we go up and increase more and more operations on top of these trees, we get more complicated and more descriptive expressions. And we can read these somewhat by saying that all nodes represents either functions if it's not a leaf node or not at the bottom of these trees, and all variables or constants are these leaf nodes here. One can think of variables or as constants as a variable with just a constant value set to whatever the name of that variable is. We can think of the edges of these trees as function compositions. So for example, if we define g of x of y to be this multiplication operator, once we add this sine of x on top of it and declare that to be f of x, then this underlying expression is essentially f of g of x of y. And we can define this overall as h and x and y. Importantly, it also allows us to define things such as values, expressions, units, and ranges recursively by going down these trees. What makes SISSO fairly unique in the symbolic regression landscape is that it's a deterministic way of finding these expressions. How it does this is that it uses a feature creation step in order to generate a library of billions or trillions of candidate descriptors, and then uses compressed sensing to find the best 1, 2, or 3 of these candidate descriptors to describe some target property. This is why we typically call SISSO to be a combination of symbolic regression and compressed sensing, where the final vector and model that we get is essentially a set of these candidate descriptors merged together in some type of linear model. In the first step, of SISSO is always going to be to build up our library of candidate descriptors. For this, a user only has to define a set of operators, here shown as the sign of x and multiplication in as blue and green respectively, and some set of primary features or leaf nodes on these trees, here shown as a time feature in orange and a frequency feature in purple. We then start applying the operators onto the primary features and previously generated features recursively following some physical law. So for example, for rung 1, there's only one valid candidate descriptor that can be generated from this, mainly the multiplication of this time and frequency term. This is because both of these are united quantities, and taking the sign of a united quantity doesn't make physical sense. Well, we can do it mathematically. Nobody has defined what the sign of a second is, so therefore you can't really do it in a physical mindset. However, once you multiply these two features together, the unit cancels out. So for rung 2, we can actually start to take the sign of it, as well as continue on these multiplication trees here, where essentially we've taken this rung 1 feature and multiplied on the two primary features. And this can continue for as long as possible until we realistically hit a computational limit of how many of these trees we can store on a computer, or how many trees we can feasibly scan through in a reasonable amount of time. In SISSO, we always define and reference these features as the root node of our binary expression trees, here shown in this thicker border. And the height of the root node essentially corresponds directly to rung. So rung 0 always corresponds to primary features only. And then essentially rung 1 and 2 is one level up or two levels up from this primary feature. As well as by addressing these root nodes directly, we can define everything from the candidate descriptor as a recursive function defined from this operation here, and properties passed from the user in its initial data collection phase for the expressions, the unit, the range, and the values, where these three terms here shown in the node are all things defined in our column header of our data file. The reason why this is important is we can now keep track of a lot of physically relevant information, and that provides us ways of adding on grammatical rules for symbolic regression. The first one that we actually implemented was known as units, and making sure that the candidate descriptors themselves are physically meaningful terms. What I mean here is that if you have some dimension to object or property A and some dimension to property B, physically they must follow some rules in order to be combined. Here we can actually keep track of that by first defining different units for different operators by combining them in this way. So unit is essentially a multiplicative algebra system. So that means that for addition and subtraction, the unit of A plus B will simply be the unit of A, and the unit of A times B or A divided by B would essentially just be the unit of A times B and unit of A divided by the unit of B. For transcendental operators, we always set this to be a unitless quantity because, again, you can't really define the unit of the cosine of something. It doesn't take on units. It doesn't fit within the algebra itself. And polynomial terms are just treated as if they were multiplication or division. And we do this because we want to create restrictions on what different types of candidate descriptors are allowable. So for example, I mentioned previously that the unit of A plus the unit of B is equal to the unit of A. This is because in the code we restrict it such that the unit of A and unit of B must be exactly the same in order for it to be applied in addition. And you can think of this as you can't really take something with dimensions of distance and add it to something with dimensions of time. However, it's important to note that SISSO doesn't really understand length and times, but thinks of the unit as its own dimension, so it wouldn't really be able to add a meter with an inch, for example. An additional restriction is that all transcendental operators must only act on unitless quantities. This is just to make sure that they're physically meaningful and physically make some sense. And importantly, as you noted, might have saw in a previous slide, we're also including the range of our various features. The reason why we're doing this is because there are cases where our training data might not necessarily contain any problematic values, but in the range of possible values encompassed by that descriptor or that primary feature, problems can arise. So this is a very simple example where we're trying to find a model for y that is simply 1 over the absolute value of x. And to do this, we're training on all the large values in terms of magnitude of x, where x naught goes from a range of -5 to 5.0, and is defined as x plus some Gaussian noise term with a standard deviation of 0.025. By doing this and looking at the test set, we see that there's some very large errors here. This is because we can get very small values of x. This 0.025 Gaussian noise term can then be quite significant. And by dividing it, by doing 1 over that value, we're then further amplifying this problem, meaning that this, while the training data looks great, there's fairly massive problems on the test data set. This can even go up to nans, for example, if we have logarithms or square roots. So we allow the user to potentially define the theoretical range of a given primary feature and keep track of what the range should be by applying different algebraic terms on it. So for example, if you have a sine, the range will automatically go from -1 to 1. If you take a square root, we can define the square root of the min and the square root of the max as the possible range. For the operators, those are just examples. I'm not going to go through the entire table with you. That's in this paper here in JPhys Chem. And from this, we can now say that, okay, even though this feature here, x1, which has a larger Gaussian noise term of the train data, isn't as good, we know that the range of this particular input, 0.125 to 5, is within the domain of the previous operation shown here on this slide. So division can't contain 0, logarithms can't contain non-positive values, square roots can't contain negative, and therefore we should reject this particular model x naught in favor of x1 so we can ensure ourselves that we don't have anything very strange or wrong going on. And finally, SISSO++ has one other key advance in SISSO that allows it to address some more fundamental problems in symbolic regression. Mainly, if we think back to how we construct our feature space, there is no internal constants within these operators themselves. It's just t times omega. And then when we take the sign of that, it's just t times omega. It's sine of t times omega. What if there's a phase shift? What if there's some type of frequency shift going on? Well, if we try to pass this into SISSO itself, so this is just a sine function of x and y with some frequency and some phase shift added to it, SISSO doesn't know what to do with it because it can't actually find those expressions. Similarly here with this Lorentzian, moving it slightly off center means that it's no longer accessible for SISSO to find. So in order to get around this, we implemented a nonlinear optimization scheme that we call parametric SISSO in order to find these more complicated expressions. So how this works is that each operator has a possibility of having a scale term alpha and a shift term beta. And we define it such that there is no possibility of linear dependency. So for example, the square term, we only have beta because alpha times x squared plus beta, or x plus beta squared, is essentially the same or can be mapped onto alpha x squared plus beta. So we don't necessarily include all possible features. We exclude anything where we get linear dependencies on, and then we can store these parameters as a vector on our head node. So here we see that the x plus beta term here is beta sine 1 instead of alpha sine 0 and beta sine 0. So we can think of this as it's a parameter stored on that head node, but is associated with this squaring term. We also allow for a hyperparameter such that we can do this parameterization scheme on the entire tree or on just a head node. So if you do it only on a head node level, that means this x plus beta term is actually using what was ever stored for the nonlinear optimization of the square value here. It makes it slightly easier to do and can, in some cases, actually give you slightly better results because of various noise factors that can be going into it. And if we were to do this on a non-parameterized operator, then at the head level 1, we just completely exclude that type of operation. That's really why we have this hyperparameter, is so we can combine things with non-parameterized features and have that be fixed in stone, essentially. We can then optimize these parameters utilizing a loss function. Here, we're doing a log-based loss function in order to better handle outliers, which is a known problem in these types of situations, and then perform a local optimization using the subplex algorithm, which is a variant of the Nedler-Mead approach, where we essentially have a triangular walker trying to find a global minimum or global maximum on a landscape, shown here in this animation, where the subplex basically splits our space more efficiently to allow us to explore a larger space in a fairly efficient manner. We can then do an optional global optimization in order to make sure that our initial guess isn't locking the structure or locking the parameters into a non-optimal part of the parameter space before doing a final local optimization using the subplex algorithm again, but with slightly more stringent conditions for convergence. Doing this, we can now actually find both the Lorentzian and sine curves with fairly easy time of it. However, it is a nonlinear optimization, and in theory, these could go on forever. And unfortunately, we don't have that kind of time. So there is some limitations to it, such that if it goes for too long, we just stop it off prematurely, even though they're not converged. This has been defined in this JSChem paper here, but it's typically on the order of a few hundred iterations. This means that there are going to be some cases that are just too hard to find, such as this very high frequency sine curve or this very thin Lorentzian. And while the parametric SISSO won't perfectly match it up, we do see some type of peak structure with this methodology, as well as some type of general periodic thing, even though it's not perfect. This allows us to gain some insights through this parameterization scheme that would otherwise not be available. With our now completely generated feature space, we can now actually utilize the SISSO algorithm to find the best low-dimensional descriptor. How this works is that we screen over all all candidate descriptors against the target property utilizing some type of correlation metric, store the most correlated species or candidate descriptors in a subspace known as S1D, and trivially find the best one-dimensional descriptor from that. We can then calculate the residual of these models, screen which input features best map onto these residuals, store those into a subspace known as S2D, and by performing an L0 regularized regression on the union of these two subspaces, we can find the best two-dimensional descriptors, and this goes on until we hit some type of convergence criteria. Historically, SISSO only looked at the top model when doing this procedure. However, this isn't always going to lead to optimal results, as this very simple toy example will show you. This corresponds to a data set with 3 data points, here shown as E1, E2, and E3, essentially setting the unit vectors that spans our feature space, and 5 input features: F1, F2, F3, F4, and F5. Here, we see that the best model is going to be F1, as it has the smallest residual and highest projection score on our target property, here shown as this purple vector P. But F2 does do a fairly good job. However, if we only look at the top residuals shown here on the top, we would see that F4 and F5 are actually the 2 input features, or the 2 candidate descriptors most highly correlated to this residual here, so they would be selected, completely missing out on the fact that our F3 one here perfectly aligns with the residual from F2. This means that utilizing this multiple residual approach, we can find the optimal model more quickly than if we were to do a standard 1 residual approach, as in this very simple toy example that I made to describe this procedure or these happenings more easily, we would need to go to a 3rd dimension. However, this is in fact a hyperparameter that we cannot maximally choose the value and assume that's going to be good. This is because we have to make a choice where this projection score for SIS with multiple residuals is going to be the maximum across all of them. So we're not going to take the NSIS candidate descriptors that best map onto each residual for numerical consistency reasons. This means there are going to be cases where, for example, here, if we look at 5 residuals instead of 1, we consistently get worse performing models on 2 dimensions. This can be mitigated by just adding this as a hyperparameter that you need to optimize during hyperparameter optimization, where we see that it does significantly improve the performance of our 2D models utilizing 10 residuals. And this is comparing different SIS subspace sizes, or NSIS here. And if we go to 3-dimensional cases, we also see consistently better results. Here you might be slightly surprised. By increasing our SIS subspace, we can actually have an increase of error in 3D. This is an artifact of the underlying projection procedures that we're doing and utilizing these subspaces. For a 2-dimensional model, you always assume monotonically decreasing, or at least constant and decreasing. However, by going into, for example, a drop here, we can actually get slightly different features that pop up within these projection spaces, meaning that you could be missing out something that's important for higher dimensional models. This just means that we always have to assume that the hyperparameters for SISSO must be treated as hyperparameters, not something to just maximally increase the values of in order to just assume that's going to be good. They are, in fact, hyperparameters, and they must be optimized. Finally, we also have a consistent classification algorithm now where we perform an SVM classification procedure in order to make predictions of some type of models for the system. This is just an improvement over the simple convex hull approach that we did in previous classification schemes, where we didn't really have a way of making predictions on new data points. So it's just showing that it works for this 4-class system, where we basically just took a random sphere, cut it via planes, and then did some SVM logic to it in order to create these classes. So it is an important advancement where we now have prediction capabilities for both regression and classification problems. However, there is one very big drawback of symbolic regression is that it is an NP-hard problem with combinatorial scaling. This is best shown in the feature creation space. However, to have just one operator and two primary features, we see that rung one type of candidate descriptor, no problem. Rung two candidate descriptors, no problem. Rung three, we now have 1, 2, 3, 4, 5, 6, 7. And rung four would just continue this combinatorial train going. As we can see here, for rung four, if we go beyond 2 or 4 input features, it's real hard to justify the use of it because it's just too complicated to create all these various candidate descriptors. We also see a similar combinatorial problem in the descriptor identification step utilizing the SISSO algorithm related to the L0 regularized regression, where as we go up to fifth dimensional models, we're really restricted to roughly 50 to 100 as our NSYS select size, because otherwise the number of models that we would need to test become too great. So for example, if we were to go up to 1,000, we would essentially need an exascale computer in order just to calculate the fifth dimensional model case. And realistically, this is just impractical to do. However, these combinatorial scaling problems also have the advantage in that it's very easy to port these onto GPUs to restrict our amount of time we take in numerical parts of the code. In fact, if we were to look at a case that we purposely designed to be the least numerical, so this is from a Kaggle competition data set looking at the energy of formation for various aluminum, indium, gallium, oxide materials. There's 2,400 data points in this data set, and we set an NSYS select size to be 50,000 in order to basically maximize the amount of non-numerical work and communication-related work we would have here in the SIS step. We can get economic performance in this worst case scenario by just simply using a hybrid CPU plus GPU approach with single precision numbers. So we see a 4.71 speed up above the 4 times speed up that you would need to have as an economic break-even point, essentially. And this is a worst case scenario. We do have better results from more realistic systems. I just want to highlight the importance of utilizing modern computational tools to address some of these more fundamental algorithmic problems. And we can see that both feature creation step and L0 step, which are the more numerically heavy terms, are performing quite well. And again, if we're to use a system that has more favorable characteristics, this porting is even better. Importantly, we use Caucus in order to do this, allowing us to have a portability within our porting, so we can not just look at A100 GPUs, which we saw previously, but also AMD GPUs such as MI250s and MI300As. You notice here the MI300A is slightly longer or larger time than the MI250s and A100s. This isn't really a worse GPU performance. It's just that these nodes have slightly fewer GPUs per node than the A100 or MI250 nodes. And throughout all of this porting work, we ensure that the great MPI scaling of SISSO is preserved. So we have near linear scaling on both CPUs and GPUs up until the baseline amount of work that has to be done for all calculations. We do start to see a tail off here, but this is to be expected given various system sizes. If we were to increase the problem slightly, we would expect that the scaling would continue on ad infinitum because this is a fairly trivial scaling problem. With that, if you want to get access to the code, you can find it here in this tiny URL for the Git repository. There's this JCP paper covers most of the advances that I highlighted in the underlying algorithms. This paper here is simply an implementation paper describing the capabilities of the code and highlighting the fact that this is a very well documented code. And I'll be happy to take any questions after Lucas's talk. I hope you enjoy the rest of the session.
Okay, so thank you to Tom for this talk. And yeah, he is actually here already, so can already take questions. So we don't need to wait until after Lucas's talk. So yeah, if you want to use so for people on Zoom, want to use the Q&A feature to write your questions, or you can raise your hand and we can unmute you so you can speak with your questions. And for people watching on YouTube, you can write in the chat there, and people on Kushare can also write in the chat there, and we'll monitor these things. So yeah, I think we already do have one hand up from Reza, so I just will allow you to talk. And yes, if you can unmute when you're able and ask your question. I don't know. Yeah, Reza, if you manage to unmute and ask a question at some point, we can come back to you.
So James, can you unmute the person?
I can ask to unmute, but I can't make them unmute. So yeah, yeah, unmuted now. So yeah, Reza, if you want to ask your question, you can go ahead.
If you're trying to speak, Reza, it looks like you're hardware muted as well, potentially.
Okay, maybe Reza will come back to you afterwards. Or you can also write in the Q&A your question if you want to ask that. But we have another hand up from Sebastian, so I will just allow you to unmute and allow you to. So yeah, you can unmute Sebastian with your question.
Hi, can you hear me?
Yes, yeah, we can hear you.
Thank you for the presentation. It was really nice. I just have one question. I think I missed the detail. So with SISSO, you generate these descriptors with the functions. And how do you go from these descriptors to the model? How do you use these descriptors and transform it into a model for predictions?
Yes, let me share my screen real fast. Okay, I think my screen is being shared. Yes. That is what this step is doing here, where we generate our candidate descriptor space, and here it's represented for a very trivial problem of 3 data points. So you have 3 vectors here and 5 features with 1 property in this purple vector. We screen all of the possible descriptors and see which ones are most correlated to a given target property. Here it's F1 and F2. We store those into a subspace, in this case S1D, and then we can find the best one-dimensional descriptor by saying which one is most correlated to the target property. We then calculate the residuals. Here they are these delta vectors. See which of the input features are most correlated to a given residual, with the number of residuals being this nres hyperparameter here, so in this case 1 or 2, store those into a different subspace of S2D, and by performing an L0 regularized regression on the union of the two S1D and S2D descriptor spaces, we can find the best two-dimensional model, which is essentially just a linear regression model combining these two nonlinear features into it. And then this continues until we hit some type of n-dimensional model.
Okay, so the choice of how many levels to go, is it a parameter that we need to decide?
That is a hyperparameter that we normally set through cross-validation. So if we look at this chart, we would see that by going from a two-dimensional model to a three-dimensional model, we get a slight performance improvement. Normally, once this hits a plateau, we cut off the calculation, say that's the optimal model to ensure that there's not some type of overfitting going on.
Okay, great. Thank you.
No problem.
Thank you, Sebastian, for your question. Yeah, so we have a question in the Q&A from Vasilios Raptis. So he says, congratulations for the presentation. Is symbolic regression somehow related to the technique of grammatical evolution?
Parts of it are, I think. There are genetic programming bases for symbolic regression, which you can probably reframe as a grammatical evolution problem, but I don't know all of the details of grammatical evolution to be sure the exact one-to-one corollaries and where they differ.
Okay, thank you, Tom, for that answer. I don't see any other questions for the moment. Maybe I can ask a general question then, Tom. So you showed quite a few improvements to SISSO and SISSO++ in this presentation with these toy models or mathematical models to illustrate the improvements. But how, from like a practical point of view, do these improvements help materials discovery? Like, do you have examples where it show that these new features help with discovering new materials?
So how it basically helps, for one thing, the GPU optimization helps because it shortens down the amount of time needed to actually solve the model, so you can do this in a more robust manner, essentially. For some of the more methodological improvements, it essentially is trying to introduce more grammatical rules to the feature creation process to ensure that you don't get odd or nonsensical results. So, for example, without this domain range checking feature we're showing here, it would not be uncommon to see a single data point have errors on the order of 10 to the 25 because you just happen to be dividing by 0 or something very close to 0, and that one data point completely screws up your cross-validation check, for example. The parametric SISSO helps by allowing you to explore a more complete feature space, and units were introduced to essentially remove a common criticism of symbolic regression when applying to physical properties, in that you get expressions that, as a physicist, you say this doesn't make sense because they are combining dimensions that shouldn't be combined. They're doing things with exponentials that shouldn't be done. And this just alleviates those things.
Okay, great. Thank you. Still no hands up and question in the chat. So yeah, maybe I just ask one other general question. Oh, yeah, one other question then. So you showed this scaling behavior of SISSO when you have higher rungs on your model. Do you ever need to go really beyond rung 3 for practical purposes where you have this kind of bad scaling behavior?
That is difficult to answer because in practical terms, going beyond rung 3 is almost impossible for modern computing technology and standard feature sizes. So we can get accurate models with rung 3, but answering the question, is there any point to going beyond it? Maybe there's an even better model that that extra dimension would unlock and make more physical sense. So it's hard to answer directly in a concrete way, but typically rung 3 will give you fairly reasonable results that are in line with other regressor techniques, which imply that you're at a reasonable level of accuracy for a given data set, if that answers your question.
Yes, perfect. Thanks, Tom. So yeah, we've got one more question, and then I think we'll move on to Lucas's talk. So this is the Q&A by Xiaoyu Wang, and apologies if I pronounced your name incorrectly. So they say, thank you for your report. I tried to use SISSO, but the formula obtained is very complex and still difficult to understand. I think you mentioned that the unit limit will greatly increase the readability of the formula, which is good. Are there any other suggestions to increase the probability of acquiring readable knowledge?
Yes. So let me see if I have presentation on this available. I know I do somewhere. That should. Did my screen share change, or is it still on the presentation I gave?
Still on the one you gave.
Okay. Let's here. Okay, it should now be changed, correct?
Yes, now it's changed.
So for this model, we still have complicated formulas that are difficult to fully understand. However, you can do post-processing techniques, in this case showing the SHAP and Sobel values to get the most important input features here. And then by sampling the model over a distribution that is mapped onto your input space, you can actually understand what the expected value of your models are given a particular range here, which allows you to gain some of those more physical insights out from it beyond just looking at an analytical expression, because it is difficult for most people to see a 7 or 10 input equation and then understand intuitively what's going on. So that's why we also support these type of post-processing techniques where we can better visualize what's going on.
Okay, then yeah, thank you. Hopefully that answered your question. And yeah, thank you, Tom, again for the talk and for being here very early in the morning in Arizona to answer the question. So yeah, and now I think we can move on to Lucas's talk as well. Thank you again, Tom.